Integrals of this form, where there's a constant plus or minus the variable squared, or maybe it's the other way around, the variable squared minus a constant, can be simplified using a trigonometric substitution and then simplifying using one of the Pythagorean identities. Now, in this lecture, we're going to look at the three scenarios where this method can apply and some special considerations that you have to be aware of. And in the next lectures, we'll look at some examples and see how you can see how this material is actually used. Ultimately, there are going to be three different scenarios that you can simplify using this method. I've summarized them here along with some special considerations. Now, the first column has the three standard expressions that when you see them should make you think of using this kind of substitution. The second column has the actual substitution that you should use, and the third column shows the simplification that would be your next step based on one of the Pythagorean identities. So looking at the integral that we started off with on the last page, the integral of the square root of 4 minus x squared, that looks like this one, where a is equal to 2. So I would substitute 2 sine theta for x. And if I do that, this becomes the integral of the square root of 4 minus 4 sine squared theta dx, which is the integral of the absolute value of 2 sine theta dx. Now, this represents a little issue. In many of the integrals that we're going to see, we're going to get to this point, and we're going to want to somehow reduce the result. For example, if we get something like cosine squared over absolute value of cosine, we like to be able to reduce that to just the cosine, but the absolute value is a problem. So this is where these restrictions in the last column are going to help make things simpler. With the first substitution, if we limit theta to being between between negative pi over 2 and positive pi over 2, then we're going to get every possible value of the sine of theta over here. And the cosine, more important, the cosine with that restriction is always going to be positive. So in this case, it's going to be okay to simplify the absolute value of cosine theta to just cosine theta. And with the tangent substitution, we get the same advantage. If we restrict theta to the same range, then again, we get every possible value of the tangent, and the secant is always positive. So when necessary, we can simplify the absolute value of the secant theta to just secant theta. Now, it's when we try to do this with the last one, the secant substitution, that we run into potential issues. Right? The substitution that we'll use for the absolute value of tangent theta is going to depend on the values of theta. If theta is between 0 and pi over 2, remember that the secant is undefined at exactly pi over 2, then the tangent is positive on that range, and we can just replace the absolute value of a tangent with the tangent. Now, the downside to this is that for values of theta in this range, we only get positive x values, right? Because the secant is strictly positive. So any integral where we use this substitution would only work for values of x greater than 0. Now, on the other hand, when theta is between pi over 2 and pi, the tangent is going to be negative. And if we have an absolute value of a tangent, then we would have to replace it with negative tangent theta instead. Now, similarly, this range of values for theta is only going to give us negative x values when we take the secant of it. So this substitution would only apply for values of x less than 0. So what does this mean? Well, in practical terms, in the case where we're doing a definite integral with the secant substitution, you need to be aware of which case applies and possibly split the integral into positive and negative parts, depending on what the limits of integration are, right? So with indefinite integrals, on the other hand, your result will often have to be given as a piecewise defined function, right? One for the negative values of x, where you used one substitution for the absolute value of the tangent, and a second one for positive values of x, where you use the other substitution for the absolute value of the tangent. Unless the problem specifies a restriction on the variable, in which case you wouldn't have to worry about it at all.